Well, I think we can start. So welcome everyone. Today we are happy to have a talk by Ratul Mahanta, and he will speak about gravitational waves from high temperature strings. So please start.
Okay, so first of all, I would like to thank the organizers for giving me this opportunity to talk about our recent works. So the title of the talk is Gravitational Waves from High Temperature Strings. And so this will be based on the first paper and also these papers. So it's in sequel we have written, but I will mostly focus on our recent work. However, for a excellent summary, you can have a look in this proceeding article written by Gonzalo. So, okay, so this work has been done with my nice collaborators Andrew, Anshuman, Fernando, Gonzalo, and Francesco. Okay, so before I start, I just like to say that please interrupt me anytime you like. So, what are the motivations? The motivations I have listed here. So, gravitational waves at high frequencies are currently attracting attentions, and there are absence of known astrophysical sources if they are there. For a review of sources and proposals for experiments, you can have a look at this paper which came out from a conference workshop, I think. So as of now, none of these proposals for the detections yet achieve sensitivities to stochastic gravitational waves background of cosmological origin. Nonetheless, it is important to identify possible sources. So what about gravitational waves from highly excited strings, that is string Hagedorn phase? And also we need to contrast with the BSM predictions. Okay, so this is roughly my plan for the talk. So I will introduce the what is string Hagedorn phase, and I will discuss the Boltzmann equation approach to string thermodynamics. So this will allow us to study the out of equilibrium thermodynamics, and we will be able to compute the equilibration rate. So this part I will be brief. It's mostly from our previous paper, and then I will discuss an epoch of highly excited open and closed strings in Hagedorn space. That's the cosmology, and we'll see realistic scenarios. We'll see that from the based on the studies on the equilibration rates, we'll see that there are dominance of long open strings in during this phase or epoch, and we will study the stochastic background of high frequency gravitational waves from thermal open strings. Okay, so the first part, what is string Hagedorn phase? So the density of states in string theory has a generic exponential growth, and you can see this exponential factor here, and this we call the inverse Hagedorn temperature. It's the temperature is proportional to the string it says string scale. We'll set it to 1 for the first part of my talk. So the energy of the string is tension time length, which is same as length. In canonical ensemble, the number density has a Boltzmann suppression factor, which depends on temperature, like T, not the TH. And we can see that if you combine both the exponential from DL and this Boltzmann suppression factor, we are introduced with L, which depends on beta and beta H. So this is the temperature. Okay, you can see from here that whenever beta is less than beta h, so these are the inverse temperatures. So the temperature is greater than Hagedorn temperature. L is negative, so there is a chance that this integral of course diverges, for temperature above the Hagedorn temperature, but we will be staying below and close to Hagedorn temperature. Then the scenario is that whether the energy density is finite or not. So for cosmological considerations, we need large, but finite energy densities. So there is a case typically when this factor A is less than equals to 2, as we approach to the Hagedorn temperature from below, this diverges, but this is known as the limiting case. And as long as we are below the Hagedorn temperature, it is always finite. So in the other case, when the energy density is actually finite, when we reach to the Hagedorn phase, there phase transition happens, but we will not be talking about that. We will be considering the limiting case. So in this scenario, it is what we from now on I will be referring as the Hagedorn phase. And in this scenario, gas of long strings dominate.
Excuse me, Ratul, what is the A? What is the parameter A?
It depends on compactifications also. So it's the generic behavior I am for example, it's just 1 if all the 9 dimensions are compact. So I am saying that it's just generic behavior I am showing here. Yeah.
Mm-hmm.
Yeah. Can you see my cursor? It's.
Yes.
Okay. I was just nodding. Okay. So we'll see that these long strings dominate. So this is the. Okay. So I'll motivate it in only flat space toroidal compactifications. For closed strings, the energy has these components. First of all, there is a special momenta in the non-compact dimensions, and DC is the number of compact dimensions, and for them we will have the KK and winding modes. However, since there is a growth of the density of state that comes from the oscillator modes, and this because many oscillators can populate to a fixed NL plus NR, which are the left and right moving oscillator levels. So for fixed values of this quantity, there are Ramanujan partitions of these integers appear, which diverges for which has an exponential growth for large values of n. So that's what we mean that long strings dominate. So roughly, like it's behaves like a non-relativistic particle, massive particle, compared to the momentum and other modes like KK and winding modes. But these details can be found in our old paper. Okay. Okay, so long strings can split, they can join, intersect, etc. But typical strings are non-relativistic. Typical means we will be fixing the mass or length, and we will be summing over all possible, we will be averaging over all possible states. So in thermodynamics, it's a coarse-grained behavior, and that's what matters. So we will be calling it typical strings. I will make many of these things more precise later. So when I enter in the next part of my talk, which is likely on the recent paper. But for just to introduce, okay, so they are non-relativistic, and there is a conservation of mass or length in these interactions. For example, if a closed strings decays to two daughter closed strings, this L prime and the length of these two add up to the mother string. So that I would what I mean by conservation of mass is a good approximation. And we need to think of what dimensions are effectively non-compact, although there could be many compact dimensions, but some of them can be behave like non-compact whenever it is large enough for a typical string to perceive it as non-compact. Okay, so I'll make it clear. So there is an interpretation of these long strings in terms of random walk by many people, including Manes. So the long strings are in random walk configurations. And we know that a long string of length L in this spatial dimension effectively occupies a volume L to the power d by 2. You can think of as the as a part dimension, it's square root L. So it comes from the, of course, in random walk, average length is, after say n step of walk, the average length is 0, because there is a equal probability to go in the both right and left. But the RMS length is goes as square root L part dimension. So this is the factor. So whenever this is the volume occupied by the string is less than the volume, then we'll perceive the space as non-compact. However, whenever this is very, very large compared to the volume, we'll see call it effectively compact space. And strings effectively occupies the entire volume V for the compact space. So this is what we mean by compact and non-compact. But when we will be dealing with cosmology, we will be sticking to scenarios where there is exactly 3 spatial non-compact dimensions for realistic models. Okay, so the more on the random walk interpretation, decay rates of typical strings like the coarse-grained average over all possible oscillator modes for a fixed mass or length. In D non-compact spatial dimensions, we have a for self interaction, the decay rate is this. And it's computed from the worldsheet computations. However, here I will only try to interpret it in the random walk interpretations. So you can see that it is a length conserving process. And we know that the probability of a random walk of n steps to come back to its origin goes as n to the power minus d by 2 in d dimensions. So you can, this number of steps is proportional to the length, because in each step you move in some fixed distance, some unit distance. So therefore proportional L to the power minus d by 2. So you can compute it in 1D. It's easy to see, because n step you have to take n by 2 of forward step and n by 2 of backward steps, then you will come back. So that's what closed strings mean. They should come back to its a point. And this is the combinatorial factor in the probability. And this goes as square root n for one dimension and large n. So you can now interpret this factor, also this L, because as I said that closing points, or you can think of that these intersections, like intersecting, they can intersect at any point in the closed strings. So if the closed strings is large, then it's more probability. So there is also a factor of L, and this can be interpreted in a conditional probability that once we know the it's happening at some point, and L goes to dissects into two part. So it's roughly proportional to the volumes, and since it is conditional probability, the probability of the mother string go in the denominator, which will make it in the top with a plus d by 2. So okay, so I'll not go into much detail here because we'll not be needing this, but for this talk. So, the upshot is random walk interpretation allows us to interpret the decay rates, and we have in our previous paper we have conjectured the form of interactions rates which are not there in the literature from the worldsheet computations. For example, this open string decays to open plus close, and using such interaction rates, one will be able to write Boltzmann equation. That's what we have done for many situations, including this one, which we'll be using, like the interacting open and closed strings in presence of space filling branes in 3 spatial dimensions, I should say. So, okay, just to close on the Boltzmann equation discussions, I have given here a toy model due to Loewe and Thoralesius. And this is for interacting closed strings with when all directions are compact, which I was talking about. And you can see that there is a L inverse. So the factor you are asking for A is minus 1. And this can there can also be some model dependencies and etc. We'll see. So these like not in flat space. So far we are talking about flat space computations. Once we know the equilibration rate, so we will be comparing it with the Hubble scale, and we will talk about cosmology. Okay, so this is the number per like it's okay. So it's the number of strings between L to L plus DL, and there is a distribution, like there is an evolution equation, and we can interpret it in strings joining and splitting like closed strings. I will not go into the interpretations. But thing is that there is a equilibrium configuration, which means that the time dependence on the left hand side go away, it's equals to 0. And basically it tells us that we have to think of the detail balance, that each of the quantity in the parentheses is set to 0. That's what an interesting phenomena in this Boltzmann equation approach. And when we take the perturbations around the equilibrium configurations, we can read off the decay rate. Of course, in this model, we have a for this equilibrium rate. So this we have a here only I have stated the late time behavior, but we have an analytic solution for this, but I am not presenting it here because most realistic this is a toy model. Yes, realistic situations, these Boltzmann equations are lengthy, and also this is also complicated, and we have a lack of analytic solutions, but we can always read off the equilibration rate. So okay, so that's the thing that we can compute the equilibration rates in Boltzmann equation approach to the string thermodynamics. Okay, so I will switch to the second part. But if you have any questions, please let me know till now.
Could you probably summarize like what was happening physically? So this equilibration rate, so it's essentially about how many like strings of which lenses are created and well, destroyed, and then what you set to, well, probably set to zero, considering that you have thermal equilibrium.
Yeah, so there is a quantity delta E. So as long as this is zero, so roughly this is the in setting these to zero means it's zero energy perturbation. So we are not adding energy to the ensemble. But suppose they are not settled down to equilibrium, still they are like not properly. I mean, they are perturbed around. I would say they are perturbed around a thermal equilibrium. Then whatever be the perturbations, these fluctuations go away for with a equilibration rate which is length dependent. So physically this means that when we are talking about a system of interacting strings, what is the stability of these? And this will be important because in cosmology there is a tension, like there is a Hubble expansion, and whenever it expands, the universe dilutes, and maybe some of them are not interacting, and always there is a well, I should say that we will be dealing with number densities. That's also whether some equilibration can happen or not, we need to know these equilibration rates. But these are flat space computations which we will be comparing with the Hubble scale, because I'll say because lack of understanding of the string thermodynamics in a curved background.
So
does this make sense? Yeah.
Sorry, do I understand correctly that if it was just a thermal equilibrium, then everything is decided by this Boltzmann formula?
Yeah.
But if you want to depart from it, then you need to take into account interaction, and this explains to you how fast it goes back, right?
Yeah. For example, if you give a if it is not non-zero finite energy perturbations, then they never goes back to the old configurations. So only the zero energy perturbations settle to the equilibrium configurations. So that's what we have found.
Can you remind what is kappa, what is L large?
Okay, that's there is a G string square. So whenever the closed strings, the interactions happen in the bulk of the string. And for open strings, for open strings, they can interact by dissecting or intersecting the branes. So in string perturbation theory, there are some coupling constant for closed strings. In the anything happens in the bulk, for example, even here that these two joins and make something, so it's goes as G string square. But anything happens at the end point in string perturbation, it's proportional to GS. So for this case, this kappa is some parameter that depends on the G string square.
And what is L large?
What is
large.
this L?
Large. Yeah.
Okay, so this is what I have discussed here. It's
okay.
This,
thanks.
yeah.
Okay. And also string unit means couple of orders of magnitude below the Planck scale, right?
Sorry, I did not.
String units means 10 to the 15 GeV or 10 to the 17 GeV in physical units. You work
Yes.
units, right?
I think we'll see, we'll be around 10 to the power around that scale at end. But it's we'll treat them as a model dependent parameter. So what is said to us is the Planck scale, the 4D Planck scale, that is the reduced Planck scale is 10 to the power. We'll see that there 10 to the power 18 GeV, but we'll use this as a parameter. We'll see this in the next section when I will be discussing the cosmology.
So your equilibration rate basically is Planckian, and everything is basically Planckian.
Yeah, there will be suppression factors like Planck suppressions, and like M string by M Planck that will be appearing in the. Okay, yeah, we'll see.
Okay,
in the,
thank you.
I'll be more detailed in the cosmology part. Yeah.
Thank you.
So okay, thank you for. Yes.
So you had this random walk discussion.
Yeah.
And I don't know, it seems to me that it's applicable only when you have off-shell strings, right? Because
no, it's
otherwise you have energy. So like if you have this temperature, then they're weighted. Some configuration are more preferable than the others. So it's not just random.
what do you mean by off-shell string? Because
I mean,
we
they
are
do not
maintaining.
satisfy any equations of motion. They're not associated with like any energy. Because like if you have, well,
no, I think we are satisfying this relation. Just like we will be satisfying like these energy relations which are making them on shell, but we are considering that they are very large or very high. Oscillator level is very high, so for that only this random walk interpretation is there. Another point is that we have, it is a coarse grain, like we need to random walk interpretation comes only when you average over all possible like for a fixed L you average over all possible oscillator combinations, like allowed states. So in that sense it is coarse grain behavior.
Okay, I see. Thank you.
Yeah. But we are maintaining these energy momentum relations always, like energy conservations in these discussions. But yeah, the details can be found in this paper. Yeah. So okay, so I should can I proceed with the now this or are there any questions?
I have a question. So what you say is more or less the same would be for cosmic strings, right? Because similar models were discussed for cosmic strings as well.
Yes, many of the random walk interpretations and etc. go and also this open string dominance and etc. are also like are there. I don't know much about them, but yeah. But once these decaded computations come like from string computations, so we will be sticking to string theory. But I think there it's also there is a parallel to cosmic strings, except the exact decaded computations.
Okay, thank you.
Okay, so if there are okay, so I will proceed. So the second part, the string Hagedorn phase in early universe. So first, I'd like to say that our GW spectrum results rely only on the string Hagedorn phase, like the limiting behavior we did, not the phase transitions, and robustly independent of how such phase was reached. Still, I would like to mention just one scenario where the universe entering an epoch of hot strings at the end of inflation, but inflation is not needed. There are a few more scenarios where this has been discussed, but to be concrete, I am just mentioning one. And the setting is type 2b compactifications. The standard model is realized on D branes at the bottom of a warped throat, not necessarily a very deep throat, but it's just a warped throat. And reheating leads to a phase of long open strings in the standard model sector. Whenever the inflation scale, the Hubble scale at the time of inflation is, or at the end of inflation, I should say, is greater than this. And here I have used, like the previous discussions are flat space. I don't need, I did not much distinguish what was the string scale, fundamental string scale versus local, but from now on I will be talking about the warp string scale. We'll see what it is, but A is a warp factor. And basically this statement is nothing but at the end of inflation, the energy density, which depends on H inf, should be such that they can produce the energy density of a long open strings, which goes as ms to the power 4. So this is that statement, and one can, okay. So, but we'll be will not be touching upon much on how this phase has been reached. Now on, I will be just dealing with the phase of hot strings rather than the how we enter to it. Okay, so the consideration will be a gas of highly excited open and closed strings in 3 non-compact spatial dimensions with ND space filling D branes. D branes may also fill some of the compact dimensions. We can allow them as these as well. Non-compact spatial dimensions are expanding due to the back reaction of this gas. So this is our metric, the 10D metric. There is a 4D expanding universe. There is a 6D internal manifold and a warp factor. Like that's the geometry we are talking about. And this gas has a well-defined canonical ensemble, in the sense of limiting behavior. Temperature approaches to the Hagedorn temperature in limit of infinite density. So we have employed the, just a minute. Yeah, we have employed Boltzmann equation approach to the thermodynamics to go out of equilibrium. And thermal equilibrium in cosmology is an approximate notion. And of course, our development in the Boltzmann equation formalism was in flat space. But the flat space equilibration rates should be very, very greater than the Hubble scale. And then we can talk about the cosmology. Okay, so I will be I will just first tell you the key features, and then I will give some details, but details can be found in the recent paper. Yeah. So longer strings return to equilibrium faster. We have seen that the decay rates depends on the length, and that's a statement. Typically, that's a key feature we have. That's we found. And in string perturbation theory, strings can split and join on D branes, and the endpoint interactions are order G string, as opposed to the interaction of 2 points in the bulk of the string, which goes as G strings square. And therefore, because of this thing, open string equilibrate among themselves and with closed strings much faster than the closed strings alone, because closed strings interactions are always with G string squared, so they are suppressed. Closed strings can equilibrate more efficiently through their interaction with open string. So whenever I will be writing the equilibration rate, it will be more clear, but these are the key features. And the energy density is dominated by long open strings, and we entered early period of early matter domination, because this long means non-relativistic and massive. So this is but it's the open string that we need to consider, and we'll see that what do I mean by the density is dominated by open strings. So, okay, so the equilibrium configurations for closed and open strings that we found is these from our Boltzmann equation analysis. So here these are densities per non-compact volume, and the special non-compact special volume, I should say. So that's what is interest in cosmology, and it's the 3 special dimension. And we have introduced the string scale, which is local. We'll see that this is related to the warp factor by this relation. So it has a warp factor in it compared to the fundamental string scale, which do not have this factor, e to the power a. Okay, and I have also just to for completeness, I have stated that these omegas are compact volume, perpendicular and along the branes, because some of the branes can also fill some of the compact dimensions. For them, the volume will be omega parallel, and the perpendicular direction, the transverse direction to the brane is volume is this. So product of this is the volume effectively occupied by the long strings in compact directions. Okay, so since we know the open string density, number density, we can multiply by L, because L is like energy, and integrate, we can get the open string density, and a closed string density. And when we mean that open string dominate the energy density, it means that the energy density of the open universe is approximately equals to that given by this, and we get this relation. We'll see that in most of the realistic compactifications, that is always maintained. I should say that you can see here that as beta approaches to beta h, the temperature approaches to the Hagedorn temperature, 1 by L becomes vanishing. So L becomes infinity. So we are below Hagedorn temperature, means the inverse temperature is just above beta h. So it is always it's large, but it will approach to infinity. So this is usually a large quantity as a function of temperature. And ND is for realistic scenarios is of the order of 5 or 10. So we'll see that this is very, very greater than this in most of the realistic scenarios. And also from the relation, because universe is dominated because of these energetics, like these conditions, which we'll need to impose, or we'll see that it's true in most of the cases. In the matter dominated era, this is the relation between Hubble scale and the density. And in order to neglect the alpha prime corrections to the expansion of the universe, we need to impose that the Hubble scale is less than the local string scale. And this quantity in the bracket is already very, very greater than 1. So and if you divide by ms, h by ms, there will be a factor of ms by mp, which should be very, very less than 1, at least hierarchically. So there is a hierarchy. So for us, the 4D Planck scale is 10 to the power 18 GeV reduced Planck mass, and the string scale, local string scale is much below them. Okay, so is it possible to maintain these conditions? Yes, possible in models with large extra dimensions and weak warping even. So this is the Jackson-Jones-Polchinski scenario. So I'll just give some details here. Long strings are localized in a small region at the tip of a throat on the internal manifold. It should not be, need not be a large throat. small throat is also fine, but they are localized on a small region in a throat. And since long in the compact dimension, these long strings are localized, the internal directions are effectively small. Like the long strings, will see that they effectively occupy the small region, but they will occupy this the full volume of this region, which is in string units order 1, but it's usually this region volume is alpha prime cube, I think. Yeah. So effective compactification volume, although we have stated that large extra dimensions, but strings are localized, so the effective compactification volume that strings see, that's what appears in our Boltzmann equation analysis, and which are order 1 quantities. And for example, like when yeah, so these are order 1 quantities. So you can see that as we are discussing that this quantity is always large, since L is large at temperature close to Hagedorn temperature, and on the other side it's around 1. So it is always maintained, but you can also interpret the other relation when you plug this of the order of 1. H by ms very, very less than 1 essentially tells that the energy of the typical long string, because this is the tension times the length. So this is the typical length. Yeah, so L has also an interpretation in thermodynamics, that at what is the length of average length of the thermodynamic system, like which is temperature dependent, and this is the thermal string, I should say. So the energy of this is less than the Planck mass, Planck energy. Yeah. So finally, I just quote the decay rates and the ratios of them to the Hubble scale. And you see that open string, open sector, and there is closed open sector, like open string can decay to closed strings and can absorb closed strings, and there is only a sector like only closed strings interactions. You can see that in most of the realistic scenario, this factor, because mostly we will be talking about this JJP scenario, these omega factors are always 1. So, and we know that we have just stated that MP by MS is very, very greater than 1. So this is usually very, very greater than 1. So open string, they equilibrate faster, and they will dominate. And you can see that for closed open sector, there is a like length dependent part, and also for large L. L can be large, but if we do the careful analysis, we can see that this quantity is also very large because of this MP by MS square L. So this is very large, and for long closed strings, they can equilibrate with the open strings, like decaying to it, or like absorbing, so this system of open and closed strings can stay in equilibrium. And finally there's a decay channel of okay, finally what will the temperature of the universe will eventually drop, and only long strings can then there is a tension, like because this L dependencies. And it is, of course, R already has a factor of GS, and it is order GS square. So the upshot is that we entered in a as I stated that closed strings can equilibrate more efficiently through their interaction with the open strings, and will enter in a long open string Hagedorn phase, because the energy density is dominated by open strings. And this is the scenario. Now the third part where we will be computing the gravity wave emissions from long open strings. Since the scenario is clear to us, we will be focusing only on the long open strings, and they can emit to massless closed strings, which includes graviton. Especially we will be using graviton vertex operators, like from literature. We will be using roughly for typical string, we will be averaging over initial state at given mass level, and we will sum over the final state, because we only care about the graviton production of a particular state, like momentum and polarization, but we should be averaging over L prime, like the daughter string, and then would be integrating over all possible length L prime, because whatever contributes to the fixed state for V. So okay, so this is and there is a absence of worldsheet description of for compactifications with warping plus flux and other ingredients needed for moduli stabilization. So we'll soon rely on a simplified scenario. But yeah, so before going to the third part of my talk, maybe if you have any questions, I'd be happy to answer. I'll try to answer.
You consider inflation with very high scale, like the Hubble scale equals to string scale squared divided by Planck mass, right? So you typically have gravitational waves produced during inflation. So did you compare your gravitational waves from strings to the gravitational waves produced during inflation?
Well, so you can, well, this is inflation should be before we should enter in a Hagedorn phase before BBN, so that we have some observable consequence. But you can think of that other way also, like the this local string scale can be even very small, but it's true that we have compared the gravitational waves with the those predicted by standard models during the reheating period. And yeah, we have if you mean that we have compared that, like.
No, I mean gravitational waves produced during inflation. During inflation, you have the amplitude of gravitational waves, stochastic gravitational waves, with amplitude proportional to the inflationary scale. Because inflationary scale is the clocking temperature of the de Sitter universe, right?
Sorry, please.
Yeah. The inflation is the de Sitter expansion of the universe.
Yeah,
right?
Yeah, yes.
And in the de Sitter expansion, roughly in de Sitter, that kind of temperature is H inflation, right? Divided by 2 pi. And the gravitational waves are produced during inflation, during the accelerated expansion of the universe.
I see.
Did you consider this kind of?
No, as of now we have not. Like what if I have understood what you are saying? So you are saying that because of the inflation, there would be perturbations in the density, and that can lead to gravity waves, and we have not considered those.
There are perturbations. Yeah. So
yeah.
So inflation produces different kinds of perturbations, including gravitational field perturbations.
I see. Yeah, so no, we have not compared with those, but since like inflation is not only way we can end up in a hot like epoch of hot strings. So maybe we can go around these things, or maybe I should ask my collaborators if they know an answer to this. But yeah.
Okay, thank you.
Okay. So we don't need inflation as a we just need to enter in a Hagedorn phase. Even it's if it is possible without inflation, it's also a good scenario for us. But no. So basically, we are talking about only reheating period. So we have compared the gravitational waves coming from the reheating period due to standard model or BSM predictions, but not with the ones you are saying. Another thing is that if there are gravitational waves during inflations, my question is that inflation is a large expansion, rapid expansion. So will not those fluctuations be diluted?
You asked a question. I should answer. Okay, so the perturbations produced during inflations are basically quantum fluctuations of quantum fields in vacuum. So inflation just is an accelerated expansion. So it takes these vacuum fluctuations and it expands them, so they are larger than the Hubble scale during inflation. And then during the next stages of the universe, they enter the horizon and they become the alive gravitational waves inside our universe. So gravitational waves are produced during inflation. The question is, what is the difference between your stochastic gravitational waves and those ones? I just wanted to ask this question.
Okay, so I would expect that okay, first of all, I don't have the answer, but what I would expect that these are large fluctuations, but whenever they emit gravitational waves, due to the rapid expansion of the universe, I mean gravitational waves are the massless modes, they do not thermalize and they will just free stream, and because of rapid expansion they may dilute the gravitational wave sector from the although there is large density perturbation, but the gravitational wave density in the gravitational wave will in any dark sector, in any radiation sector, there is a BBN bound for the density. So I am assuming that they maintain the BBN bound, but they are probably diluted compared to our scenario, because we are post inflation. If you take this inflationary scenario, then it's not that diluted. Another thing is that any gravitational decay is always Bremsstrahlung, not like us. String can decay to it's a decay, but gravitational processes are always legs which have some Bremsstrahlung, say anything we write coupled to gravity, but they are always suppressed by coupling. So that nature might be there as well. So they may be suppressed, but I honestly, I don't know. Yeah, I'll think about it.
Okay, thank you.
Okay. Okay, so thank you for the questions. I'll now talk about the gravitational wave emission from long open strings. And as I said, that there is a lack of wall-sheet description for with warping. What we'll be studying is just to get the factors correct, like the warp factors and scales, local string scales correct. It's a quantum mechanical thing, like light interacts with matter, and so as in a quantum mechanical setup we will study them. The setup is we study a graviton emission from a non-relativistic fundamental string with a tension of alpha prime inverse, and this is minimally coupled to 10D gravity. with a 10D metric, where the 4D metric is a perturbation of the Minkowski metric. So this is our setup. I am not writing the 10D action, but when you integrate over the y direction, the resulting 4D action contains a sector in gravitation and a graviton and fundamental string and the interaction term. I'll flash these actions soon, but let me say that one can compute the S matrix element for string decaying to graviton, expanding the H in terms of creation and annihilation operator. So, and the S matrix element can be computed in time dependent perturbation theory. So it's a really quantum mechanical analysis. We have adopted from lecture notes or book by Weinberg. I forgot. It's the reference is there in our paper. So, but in our setup, okay, that was for light interacting with matter. But in our setup, there will be a string interacting with the coupled to the 10D gravity. When you compactify, you will get kinetic term for the gravitons, and there is a sector for the fundamental string, and there is a coupling to the string couples to the gravity. So the upshot is that how the 4D length, like the Planck mass, the Planck scale appears. So this is we'll be considering at 10 to the power 18 GeV, but there are possibilities on like so this is roughly goes as the volume of the warped region, because it is the integral over the volume of the compactification manifold, not the volume of the warped region, because we know that contributions from the warped regions to the warped volume is typically negligible. So you can think of that it is the 10D Planck mass times the volume of the extra dimension. So it depends on large volume, what you consider that the fundamental string scale can be very large, but we'll see that what appears in our gravity wave spectrum is the local string scale, because of like we have also like the Jackson-Jones-Polchinski setup. We have they have concluded that the string in the extra dimension has a small spread in the compact dimensions around, say, a point y naught, which is typically a local minima. It's it is because that in warp thought typically A is negative, so and then it becomes positive when or go to 0. So it has a minima, and so at the tip of throat is like this minima, or say you can say that it's a small spread in the compact dimension. So that's what we have taken out, and this is the local string scale compared to the fundamental string scale, which is just 1 by square root alpha prime, and this will appear in our gravity wave sector. The upshot is that before that I should say that there is a canonical normalization. You can see that this MP should be included in H, so that the graviton sector is a field theory canonical normalization for the kinetic term, and therefore there will be a suppression by M Planck in the interaction term. Okay, so if you compute we'll not be computing it, but the fundamental string transitions from a state string state A to another string B through an emission of a graviton. The amplitude goes as with this matrix element, and from time dependent perturbation theory one can show this. The thing is that all the effect of compactification, the warp compactification is there. The rest of the part is a flat space computation, because this in these dimensional reductions what we did, this gamma hat is the pullback of just the Minkowski metric, not the G mu nu in the 4 dimensions. So this is a flat space computations. Decay rate of typical string into gravitons been computed in bosonic and superstring cases. At only the leading behavior is typical, means they have done the, as I said, that there should be a summing over, averaging over, and sum for the final state, averaging over the initial states. And so it has been computed by these people. We'll just be using those results, and that's in flat background, but the what factors is will be in this fashion. Okay, so here I am just giving the result, the graviton emission rate of at angular frequency omega from long open string of length L is given by these. The typical strings, radius massless strings like gray bodies at Hagedorn temperature, we can see that there is a, if you compare with the black body, you will find a gray body factor. We will talk about that soon. And there is a suppression. The strength of this is related to ms by mp, and this A is convention dependent, because what's the full relation of, say, TH, the Hagedorn temperature with alpha prime. So there are some factors, and it's convention dependent. We have it's order 1 quantity. We have kept it here, especially the way we will parameterize the Hagedorn temperature with respect to the alpha prime. A will be ordered 1. Okay. So measuring gravitational waves from the Hagedorn phase would provide information about local string scale ms, because that appears in the decay rate, but not the fundamental string scale, and that's the compactification effects. Okay, so also we should interpret the single power of L, each local segment. So if you take another derivative with respect to L, so the decay rate is constant. So with respect to L, as if that each local segments emits graviton independently of rest of the string. So as if the string interactions are local processes, like for long strings it makes sense, because it happens at some point in a space-time region where the strings intersect or join. So that's what we are also getting in from the computations of these people. Nonetheless, we'll parameterize emission spectrum, accounting possible corrections, and also other dependence of L. We'll see where from they can come, but we'll just to be general, we'll parameterize these things. Okay. Another thing I should say, that the produced graviton never thermalize, because if you compute the total production rate, so this is the decay rate, you will be multiplying by the number density and integrating over L, you will find, and Havel we have already computed in the open string dominated era. So the ratio goes like this, and this is exactly the H by ms, and we have set it to very, very less than 1. So they never thermalize. This massless decay never thermalize, and also it's consistent with the we have said this to neglect alpha prime corrections to the expansion of the universe. So in that scenario, like these massless modes do not thermalize, and this leads to a stochastic background of gravity waves. So first of all, stochastic means it's like background noise, like they are not they are coming from decays of strings, open strings to closed strings modes like gravitons, and there are superpositions of those signals. So this is a this background is this is a background. So this is a not like something very correlated coming from the merger problems. Okay, so I will go to the spectrum of these gravitational waves. So in cosmological gravitational wave backgrounds are usually expressed in terms of their fractional energy density per logarithmic frequency interval. For some reason, people like this, and this is the quantity h square omega h is I think 0.7. It depends on the Hubble constant today. Rho c is the critical density and of the universe today, and this quantity is defined from the total gravitational wave density with a per logarithmic frequency interval. So that's what people compute, and there is a they are stochastic, like they produce and they free stream and they never thermalize. There is a evolution equation like a rate shifting like radiation, and there is a source term because during the like there is a source term because the long strings are decaying to sourcing the gravity waves for some period of time. So it's local in time. This is a differential equation. We have not integrated over time, but we will be integrating over time, say from some starting Hagedorn phase to an ending point. So it's some time range, but we'll talk about those later. But here is a LC we have taken into account because our descriptions was always for long strings. So all the calculations we did make sense only when there is a cutoff, and in the previous paper we have computed what should be. It is around, if I remember correctly, it's I think 9 ms, 9 times ms or something around that. But there is a cutoff, and even if there is no cutoff, this although we do not expect that these random walk interpretations and etc will be valid for short strings, but even if there is no cutoff, but there is a fundamental length for strings that should be there. But we are taking it more than that, like more than ms. It's around 9 ms. Okay, so we can use this evaluation equation and integrate things using a decay rate. We have shown a decay rate, but we will be taking a more general decay rate. There is a gray body factor. It is exactly a black body. This factor is exactly a black body radiation, but the gray body factor is there. For example, B equals to 2 and sigma 1 we can compute. I should have written here, but that leads to the computations of Mati Rusho and Kawamoto Matsuo, especially Kawamoto and Matsuo, because they have done the supersymmetric case, and that's what we have taken. So, but this B, to accommodate model dependence, like compactification models, like we are in toroidal compactifications, we are talking about, like they have been computed in flat space toroidal background, but if there is any model dependence, and also alpha prime corrections, because if effects of fluxes, like we discussed our scenario, like where we end up that we should be scaling by ms and m Planck exactly with these fashions, but there are to start with, we need to deal with also fluxes in 10D to source the warp factor, and they will also couple to gravity, and there could be some effects. So these B should parameterize them, and okay, so the result is that the spectrum after integrating out this evolution equation is the results are universal as long as above rate falls off exponentially at large omega. So this is already there is a suppression factor, but the sigma should be just polynomially bounded. So And this is what is the case for the decay rates we have. So, but otherwise, I would just like to mention that these are robust. And here I give you the spectrum. And there is a part yeah, so this is the fractional energy density today for the photon. That we know, it's forgot the value, but that's known to us. Nd is typically around 5. Ls and Ln time ms, so it's the ending of the Hagedorn phase. We have said around 5, but you can vary. Usually the results are robust. The details can be found in our paper. Here I have not said anything, but to draw the plots, I'll set choose some values, but I'm just telling what are the typical values. And this G and X comes from the entropy conservations, end of gravitational, end of Hagedorn phase to today. And it has because at end we can integrate it during, because we have a source term, we can integrate it during the some starting point to some ending point, then we have to free stream to today. That's what we have to compute here. Like this is the density today, so this will appear like the CMB temperature today and everything. We have expressed quantities in terms of today. And there is a G is like the number of ratios to the relativistic degrees of freedom for today to that end. So if it is the reheating period, like normal reheating period, so we know that GS times X should be like 0.3. And X is parameterizes the effect of entropy injection during this period and deviations from standard cosmology following the Hagedorn phase. So all the effect, like you see that the omega dependence comes through this function written in blue. So that's the frequency dependence, and it does not depend on the local string scale. However, the amplitude does, but the peak of the distribution does not depend on the local string scale. And this local string scale is and I should say that also these parameters like this is typically very large, but it also depends on G and X. So the whether the standard cosmology is followed post Hagedorn phase or not. So okay, so for standard cosmology, like following the Hagedorn phase, we have plotted the also we have set, as I said, that the ms we have used as a parameter. So we have set it like 10 to the power minus 4 times Max Planck to 10 to the power minus 8 times Max Planck. But I have also quoted the standard model predictions, which is basically, so this amplitude is depends on the string scales, and they are quite higher. So okay, so the solid curves are the GW spectra for the Hagedorn phase, followed by standard cosmology with different values of Hagedorn temperature. Dashed curve is the GW spectra for the standard model with different reheating temperature, same as the Hagedorn temperature, the value is same. And the black horizontal line is a rough bound from BVN, that's for the coming from the delta N effective, like the at the time of neutrino decoupling. I think there is a bound on how much radiations we can, dark radiations we can have. So there is a bound, and so you can see that the amplitude from the standard model predictions are way higher. And this is because standard model processes are always Bremsstrahlung, because string processor, decay processes, they are directly in terms of coupling, they are string like standard model, or well, I should say that the BSM processes, the amplitude is much smaller, like even smaller than that. So standard model and BSM, beyond standard model, this is the generic plot I have. It's for standard model, but for BSM it's much lower, but I do not know much details on those studies. But yeah, we got because of they are always like 4 point like they are the graviton emissions are coming from extra legs in the standard model or BSM physics coupled to gravity, and they are always suppressed in the amplitude. Okay, so the spectra peak at 60 gigahertz for the Hagedorn phase, which is close to the result of the standard model. The amplitude of the string signal is significantly stronger than the typical expectation from the reheating epoch of the standard model or BSM theories, which are studied in this. You can have a look like for details. And should stop by saying some future directions. We have, of course, computed the gravity wave spectra, but there could be other cosmological consequences of the epoch of string Hagedorn phase, e.g. the production of KK gravitons, and since they are massive gravitons, they comes from the compactifications, their connection should be with the dark matter, and what are the effect of Hagedorn phase to them. Emission of bulk axions. There in string theory, you know that there are form field, and there will be some axions which are associated with the volume modulus. So they would lead to a production of dark radiation. But what about this has been studied, but in string models. But what are the effects of that they are coming from string Hagedorn phase, and what are the bounds, and that can be studied. And we need a better understanding of string thermodynamics in curved backgrounds. Our analyses are always in flat and then comparing with Hubble, but can we analyze the string thermodynamics directly at curved backgrounds? We should look at that at some point. And under this question, what we have not touched upon at all, under what circumstances does the universe enter into an epoch of Hagedorn cosmology? Now, I should also mention here that we have conjectured some decay rates which are from random walk interpretations, of course semi-inclusive average decay rates, but from worldsheet computations those have not been computed. If those can be verified, would also be nice. So I thank you for your kind attention.
Thank you. Are there any questions? Concerning like the last slides, so are you essentially saying that you have well, essentially observational prediction for string theory? Well, because the signal is much stronger than.
Yes. Yeah.
Yeah, well, so essentially that can be used as experimental proof of string theory. Right?
Yes. That's the it's very interesting that we can actually measuring the GWs arising from Hagedorn phase would provide information about the local string scale. Yeah, so that's very exciting result in my opinion. Yeah.
And qualitatively, can you explain why like the contribution is so different, like by so many orders of magnitude? Is it because?
Yeah, it's because well, I don't know about this. I mean, computations. Only thing I know that they are computations. These behavior is there, like MS by MP, but they got just T reheating by MP. But the amplitude itself, and that's what we are setting. Like our temperature is like both are at the same temperature, but what they have is the amplitude which is smaller, because they are always like this standard model or beyond standard model coupled to gravity. Anything coupled to gravity, that source energy momentum tensor can decay to gravitons, but it's always to Bremsstrahlung process, like not a decay process. So they are actually suppressed by factors of coupling, like the coupling they have in that scale.
But well, string theory assumes to have standard model, right, as a subsector. So with the same couplings, right?
Yeah, so that's what we are the thing that at some point what will happen, like how this phase will end. So we can see that when this phase ends, like the only the long string massless modes will be there, and they will form the standard model or its BSM model degrees of freedom. So in a sense they are also content, and both are there in our models, but the string things are like we can like if we detect something. See, to detect this, we have to be more, we need to have more efficient detectors. But even if we reach around something 10 to the power minus 7 of amplitude, then we'll be able, if we see them, then it will be talking about, it will say some information about the local string scale. So yes, they are contained in this, in the string model as well.
And can you also say like what we can measure currently, like?
Okay, so that's also a part I don't know much, but I should. My understanding is that none of there are proposals and like and experiments in this frequency range. None of them achieve the sensitivities to that amplitude, but like I don't know. I think it's sometime soon, maybe. Yeah, but
like even very approximately, how far away we are in terms of.
I have no idea, but I think it has been discussed in the review here, because I remember Gonzalo's talk. He has given a set of list for this possible experience. I myself did not search for it. I mean, there is a sorry, I probably have no answer for this.
Okay, thanks. Are there any further questions? Okay, since we don't have any further questions, let's thank the speaker. Thank you.
Thank you.